Welcome to today's Explainer. We're jumping right into a really fascinating two-part puzzle today that deals with the very nervous system of modern enterprise networks. First, we're going to figure out how to bridge disparate routing protocols so our legacy systems can actually talk to each other. And then, we're going to upgrade our digital highways entirely by diving into the rollout of IPv6. Let's get into it.
Okay, let's dive into this with a real-world scenario. Picture this. Your company just merged with another. Your network speaks EIGRP, but the new branch exclusively speaks OSPF. By default, these are completely isolated routing languages. They literally cannot exchange network maps on their own, which means users in one building cannot reach servers in the other. So we desperately need a way to make them communicate seamlessly.
Here's our roadmap for today. We'll be looking at translating between routing domains, avoiding common routing pitfalls, configuring route redistribution, the massive shift to IPv6, and finally, dynamic routing in IPv6.
All right, Section 1, translating between routing domains, focusing on the purpose and the challenges.
So, think of route redistribution as a highly skilled translator standing right at the border of two merging networks. It's the process of grabbing routes learned from one protocol, like that internal EIGRP network we just talked about, and seamlessly injecting them into another, like the OSPF branch. When you configure this correctly on a boundary router, it enables flawless end-to-end connectivity across completely different administrative domains. It's a real game changer.
Moving on to Section 2, avoiding common routing pitfalls, or as I like to call it, keeping the peace.
Here is the catch, though. Our routing translator? It isn't perfect. Without some strict ground rules, you're risking a network version of Groundhog Day, a routing loop. A route gets passed from OSPF to EIGRP and then mistakenly handed right back, just looping endlessly. The absolute biggest culprit here is unfiltered mutual redistribution. If both sides are just yelling their routes at each other without any tags, you build this devastating echo chamber that can literally bring your entire network down.
Now, what's really interesting is the root cause of all this chaos. It boils down to a fundamental language mismatch between how these protocols calculate their metrics. RIP just counts hops. OSPF calculates cost based on bandwidth. EIGRP uses this whole complex composite metric. You simply cannot directly translate an OSPF cost of 50 into a RIP hop count. It's comparing apples to oranges.
Because of that massive metric mismatch, we have to provide a sort of Rosetta Stone. In networking, that's known as a seed metric. This is a mandatory, manually configured baseline. So you pull a static route into EIGRP, you have to tell EIGRP exactly what its starting metric should be. If you skip this step, the receiving protocol just shrugs, won't understand the route, and drops it entirely.
Section 3. Configuring route redistribution. Let's look at the practical steps.
Knowing the theory, let's actually look at the syntax on Cisco routers. The logic is beautifully straightforward. First, you hop into the routing process you want to inject routes into. Second, you use the redistribute command. Now see that subnets keyword? That is absolutely crucial. If you leave that out when pulling routes into OSPF, only classful major networks get redistributed and you lose all your specific subnet data. Finally, you just attach that seed metric we just talked about.
To stop those nasty routing loops dead in their tracks, we use route maps to tag our routes. If a route gets tagged, we're basically telling the router, hey, never send this back where it came from. We also need to manage administrative distance, or AD. Think of AD like a trustworthiness score, where a lower number wins, kind of like golf. OSPF has an AD of 110, while RIP is 120. By tweaking that AD, we can control exactly which protocol's route the router trusts more when there's a conflict.
All right, let's shift gears for Section 4, the shift to IPv6, our infrastructure upgrade.
Having mastered the art of translating legacy IPv4 domains, it is time for a full-on infrastructure upgrade. IPv6 fundamentally changes how we categorize addresses. We've got Global Unicast for standard public routing, Unique Local, which does the exact same job as our old private IPv4 addresses, and notice what's totally missing. Broadcasts. Yep, IPv6 completely eliminates legacy broadcast traffic, replacing it with highly targeted multicast delivery. But there's one address type here that really deserves your attention. The link local address. So the crucial point is this. Every single active IPv6 interface has to have a link local address, starting with that FE80 prefix just to function locally. Devices use these to find their neighbors and build routing tables way before a public address is ever assigned.
Finally, Section 5, dynamic routing in IPv6.
New rules for a new highway.
With this massive new 128-bit address space, dynamic routing protocols needed a serious overhaul. But hold on, before you touch a single protocol, you've got to remember the master switch. The global command IPv6 unicast routing must be enabled. If you don't type this in first, your routers simply will not route IPv6 packets, period. It is the absolute mandatory first step.
Once IPv6 routing is actually flipped on, you're going to notice a massive shift in how we configure protocols like OSPF. Back in IPv4's OSPF-E2, we relied on those global network commands to hunt around for matching interfaces. OSPF-E3 for IPv6 throws that clunky method right out the window. Now we configure the routing protocol directly on the interface itself. It's so much cleaner, vastly improves configuration flexibility, and clearly separates our address families.
And this per-interface shift applies across the board. Both RIP Next Generation and EIGRP for IPv6 adapt their familiar IPv4 logic, but they run completely independently over IPv6. To turn on RIP-NG, you literally just go into the interface and type IPv6 RIP enable. That's it. The days of the clunky global network command are officially over in the IPv6 world.
Wow, we have covered a ton of ground today, from safely translating between those isolated IPv4 domains to laying the groundwork for clean, interface-driven IPv6 routing. So I'm going to leave you with this to ponder. Armed with unique local addresses, mandatory link local connectivity, and highly flexible protocols like OSPF3, how would you design a scalable IPv6 network for a growing business today? The tools are right there. How you build a highway is entirely up to you. Thanks for joining me on this explainer. I'll see you next time.